Hey there, and welcome to This Explainer. Today, we're going to unpack the absolute foundation of how we understand the physical universe. We'll be looking at a framework that takes the vast, abstract reality all around us and translates it into tangible, understandable numbers. Because, honestly, without this translation, science as we know it simply wouldn't exist. So, to get us started, think about this for a second. How exactly did the ancient Egyptians manage to build something as mathematically perfect as the pyramids without modern technology? Well, they actually used a unit of measurement called the cubit, which was literally just the distance from a person's elbow to the tip of their middle finger. It was a brilliant, practical solution for their time. But how do we get from a pharaoh's forearm to the remarkably precise scientific instruments we use today to study quantum physics? The answer is all about the evolution of physical quantities and measurement. To trace that evolution, here's our roadmap for today. We'll cover 1. The foundation of reality, 2. The language of measurement, 3. Navigating the extremes, 4. Adding direction to magnitude, 5. Tools of the trade, and finally, 6. The limits of precision. All right, starting right off with Section 1, the foundation of reality, why physics actually matters. Okay, let's dive into this. When you look at the sheer spectrum of human engineering, it's pretty mind-blowing. On one end, we have microscopic robots designed to fight cancer cells directly inside the human body, and on the flip side, massive rockets launching space shuttles into the cosmos. Whether it's that smartphone in your pocket, a PET scan at the hospital, or the airplane you take for a vacation, physics is literally the engine behind all modern technology. It's the most fundamental of all the sciences because it fundamentally studies matter, energy, and exactly how they interact. But here's the catch. To study the universe, we have to know what we can actually measure. This is a super important distinction. You see, physics deals strictly with physical quantities, things like length, mass, time, temperature, and density. These are elements we can clearly define, measure, and compare against a standard unit. On the other hand, we've got non-physical quantities, your favorite color, the feeling of sadness, or, the taste of an amazing meal. Those are entirely subjective. They cannot be objectively measured with an instrument. So the key takeaway here is that physics focuses 100% on the measurable world. Moving on to Section 2, the language of measurement, specifically the System International. Imagine if scientists all over the world didn't have a shared alphabet. It'd be complete chaos, right? Back in the 19th century, physical sciences were actually pretty divided and confusing. But today, we use the System International, or SI units. These are 7 base physical quantities, and absolutely everything else in physics is derived from them. We measure length in meters, mass in kilograms, time in seconds, electric current in amperes, temperature in Kelvin, amount of substance in moles, and light intensity in candela. Scientists across the entire globe agree on these exact base units, which is what allows global collaboration to truly flourish. So, if those 7 base units are our foundational alphabet, we use them to spell out complex words. And we call those derived physical quantities. You don't need to invent a totally new base unit just to measure area. You simply multiply length by length to get square meters. Want to figure out velocity? Just divide length by time, and boom, you get meters per second. We even give some of these derived units special names, like newtons for force or pascals for pressure. Literally every complex physical measurement you can think of is just a clever combination of those 7 simple base units. Which brings us to Section 3, Navigating the Extremes. We'll look at standard form and prefixes. Because let's face it, the universe, it doesn't care about human scales. Just take a look at this absolutely massive number. That's the approximate width of the observable universe in meters. It's an 88 followed by 24 zeros. Just imagine being an astrophysicist and having to write that out every single time you do a basic calculation. Not only would that take forever, but the chances of accidentally missing a single zero and completely ruining your entire experiment are huge. To fix this, scientists use something wonderfully elegant. Standard form, better known as scientific notation. Instead of writing out all those endless zeros, we just represent the number as a product of a number between 1 and 10, which we call the mantissa, and a power of 10. So that massive width of the universe effortlessly shrinks down to 8.8 times 10 to the power of 26 meters. It completely removes the clutter while preserving perfect, flawless mathematical accuracy. But physics isn't just about writing numbers down on paper. It's about communicating them out loud in conversation. And that is exactly where prefixes come into play. A prefix simply gives a proper, spoken name to a specific power of 10. So for massive, macro scales, we use terms like mega for a million or giga for a billion. This means we can comfortably chat about a national power grid generating millions of megawatts. Conversely, for the micro world, we use prefixes like micro, nano, or femto. So instead of writing out 15 decimal places, we can just casually say the diameter of a proton is 1.7 femtometers. It just makes navigating the wild extremes of our reality highly accessible.
Next up is Section 4, adding direction to magnitude, looking at scalars and vectors.
And this brilliantly illustrates why direction is so absolutely crucial. Think about it. If you tell an air traffic controller that a plane traveled 1,100 kilometers from Islamabad, they don't actually know where that plane is heading. Now, some physical quantities, called scalars, only need a magnitude, like saying a class is 45 minutes long. That's all the info you need. But other quantities, called vectors, absolutely require a direction to be completely described. Things like displacement, velocity, and force are all vectors. By establishing an arrow from Islamabad pointing exactly southwest towards Karachi, we perfectly capture both the distance, the magnitude, and the specific direction.
All right, Section 5, Tools of the Trade. Let's look at some actual measuring instruments. Sure, a standard plastic meter rule is fine if you're just drawing margins in a notebook, but it simply can't measure anything smaller than 1 millimeter. For real, laboratory-level precision, physicists turn to specialized tools like the vernier caliper and the micrometer screw gauge. Now, every measuring instrument in existence has a built-in limitation called its least count, which is just the absolute smallest value it can accurately measure. A vernier caliper typically has a least count of 0.1 millimeters, making it awesome for measuring the internal diameter of a small pipe. But if you need to measure the thickness of a single sheet of paper, you'd upgrade to the screw gauge, which has an even smaller least count of 0.01 millimeters.
Actually using these tools is a really brilliant exercise in logic. They essentially all operate on a similar two-scale system. It's a quick 3-step process. Step 1. You read the fixed main scale, just like you would with a normal ruler. Step 2. You look at the sliding secondary scale, like the vernier scale or the circular scale on a screw gauge, and you find exactly which line perfectly matches up with the main scale. Step 3. You multiply that aligning number by the tool's least count and just add it to your main reading. It is such a clever mechanical trick that allows human eyes to read tiny fractions of a millimeter without ever needing a microscope.
Finally, we arrive at Section 6, the limits of precision and dealing with errors in measurement.
Here's a bit of a reality check. No matter how good our tools get, we eventually hit a wall. In physics, error is not a bad word. It doesn't mean you messed up. Error simply means uncertainty, a margin of doubt that exists in literally every single measurement ever taken. We break these down into 2 main types. First, we have systematic errors. These are consistent flaws, like if a vernier caliper's 0 marks don't perfectly align when it's fully closed, or you just have a poor experimental setup. Systematic errors are predictable, and you can correct them. But then we have random errors. These are unpredictable fluctuations in temperature, air humidity, or even just human reaction time. You cannot completely eliminate random errors. You can only manage them.
So, how exactly do scientists manage that kind of unpredictable randomness? Take a simple pendulum. If you want to measure exactly how long it takes to complete one full swing, which is called a period, and you use a stopwatch to time just one single swing, your human reaction time is going to introduce a massive random error. Your thumb is simply too slow. To fix this, scientists take multiple measurements. They'll time 10 full swings of the pendulum and then divide that total time by 10 to find the mean. By doing this, the random variations actually balance each other out, drastically reducing the error and giving you a highly reliable measurement.
Now, this brings us to 2 words that people constantly mix up in everyday life, but which mean very different things to a physicist: precision and accuracy. Precision is all about consistency. If you weigh a book 5 times and get the exact same weight every single time, your measurement is highly precise. There is very little scatter in your data. Accuracy, on the other hand, is about truth. It's how close your measurement actually is to the true accepted value. If your super precise scale wasn't calibrated correctly, it might consistently overestimate the weight by half a kilogram. In that scenario, your results are very precise but entirely inaccurate. A good physicist always strives for both. Which leaves us with this pretty wild final thought. We've seen that our reality is measured using incredibly clever base units, precise directional vectors, and highly calibrated tools. But we've also learned that every single instrument has a least count limitation and is subject to random, uncontrollable errors. Therefore, every measurement we have ever taken of the universe is technically an approximation. So you have to ask yourself, is absolute, flawless precision even possible in our physical universe? Or is the study of physics simply humanity's beautiful, never-ending pursuit of getting closer and closer to a truth we can never perfectly touch? Think about that next time you look at the exact GPS coordinates on your smartphone. Thanks so much for joining me on this explainer, and keep questioning the reality around you.